first off, start by counting the amount of valent electrons in the molecule. As they're both halogens, and there's 1, 2, 3, 4, the valent electrons is 4 times 7, which equals 28. And arrange your atoms so that the less electronegative atom is in the middle, which is chlorine. And then you add your valent electrons, and you want to add enough to make each atom happy. So you have 8 surrounding each atom. And then check to see if that's the correct amount of valent electrons. 6, 12, 18, 19, 20, 22, 24, 26 here. So you need 2 more electrons to get to 28. So what you do is you add another lone pair to the chlorine. So now you have 2 lone pairs of chlorine, and that is your Lewis-Dot structure. The valent electrons is now 28. To determine the shape, you first need to work out the electron geometry of the molecule. So looking at the Lewis-Dot structure of ClF3, you count the amount of groups of electrons. There are 1, 2, 3 bonding pairs and 2 lone pairs, that's 4, 5 groups of electrons, which gives the electron geometry trigonal bipyramidal. And this trigonal bipyramidal looks like this. But for ClF3, it has 2 lone pairs, and 3 bonding pairs, not 5 bonding pairs. So you need to decide where the lone pairs go. And the lone pairs take 2 of the equatorial positions, as they demand more space than the bonding pairs. And so this looks like it's given a T shape. It's almost a T shape, but these 2 bonding pairs are repelled slightly downwards by the lone pairs to give an angle of less than 90 degrees between these. Possible geometry for ClF3 could be if the 2 lone pairs take the diaxial positions instead of the 2 of the equatorial positions. This would look like this. But you want to make the lone pairs happier than the bonding pairs because they oppose a stronger repulsion. And the angle between the lone pair and the bonding pair here is 90 degrees. Whereas in the other geometry, the angle between the lone pair and the bonding pair in the T shape is 120 degrees. So obviously the other geometry is a lot more favoured with the much bigger angle between the different electron pairs, and which is why this one is not observed. ClF3, there are 5 groups of electrons involved, as we've talked about. So that means there are 1, 2, 3, 4, 5 orbitals involved with the hybridization of sp3d. So start off with ClF2+. And to draw the Lewis structure, first need to work out the amount of valence electrons that should be present in the molecule. And so they're halogens, so it's 3 times 7 electrons. But then you minus 1 because it's a cation with a charge of +1. So total amount of valence electrons equals 20. And then arrange your atoms so that the Cl is in the middle. Make each each atom happy by adding in the electrons to fill the octet. And then check to see if you need to change anything and to see if the valence electrons match up with the correct amount. And so you have 6 here, 6 here is 12, 4 more electrons here, which is 16, and then 2 electrons each from the bonding pair, so that adds to 20. And you can see that's the correct amount, so that's the Lewis structure done, apart from you have to take note on the charge. And for ClF4-, the valence electrons present is for 5 times 7, but then you add 1 because it's an anion with a charge of -1, add 1 electron, and you get 36 valence electrons. And to draw this, put your less electronegative Cl in the middle, your fluorines. Make your atoms happy by adding in your electrons. And then count up the electrons to see if they match with the ones that should be present. You have 1, 2, 3, 4 times 6, 24, and then 8 from the bonding pairs, which adds up to 32 valence electrons. You obviously need to add 4 more to get to the right amount, so add 2 lone pairs to the chlorine. And then to finish it off, to make sure you know there's a charge, in square brackets with a -1 charge. To determine the shape, you need to find the electron geometry first. So you count up the amount of groups of electrons. So you have 1, 2 lone pairs, 3, 4 groups of the bonding pairs. And 4 groups of electrons means it has a tetrahedral shape, or electron geometry even. And then to decide the actual shape, you have to decide where the lone pairs have to go. So this is a tetrahedral shape, and because all of the angles are the same, you can choose any of the bonding pairs to put your lone pairs on. So just those, and this would look like and the angle here is almost 180, but because the lone pairs repel more than the bonding pairs, it pushes them down a little bit, and so this angle is less than 180. And the name of the shape is not linear, it's bent or angular. Find the name and shape of ClF4-. You count how many groups of electrons there are, and there is 1, 2, 3, 4 bonding groups and 2 lone pairs of electrons, so that's altogether 6 groups of electrons, and that gives the electron geometry octahedral. And an octahedral molecule looks like this. So we need to decide the best positions to put the lone pairs on to have the biggest amount of space between them as possible, between them and the bonding pairs. And this would mean that they would take the diaxial positions here, and therefore it would look like this. And now, because all of the bonding pairs are on the same plane, this octahedral geometry is given the name square planar for its shape.